So here's maybe the biggest question in all of physics. Where does mass actually come from? I mean, really? What if I told you the answer wasn't some crazy abstract equation, but something, well, something kind of mechanical? We are talking about one of the biggest unsolved puzzles out there, the famous mass gap, a problem so tough it's got $1 million prize on its head. And today we're diving into a radical new idea that might just crack it.
All right, here's how we're going to break it all down. First, we'll get into the mystery itself. Then we'll look at this wild new idea of reality being hardware instead of software. We'll see how the very fabric of space might be under constant stress and how that could be the key. Then comes the really fun part. We're going to try to calculate a particle's mass from scratch. After that, we'll see what this means for matter and force. And finally, we'll look at the massive challenge this whole idea poses to physics today. Let's do this. Okay, first step, the unsolved mass mystery. At the heart of it is this thing called the mass gap. Now, the name sounds a little intimidating, but the idea is actually pretty simple. It seems like there's a minimum energy cost, a price of admission, if you will, to create a particle using the strong force. You can't just make a particle with any old tiny amount of mass. Nope, there's a floor, a minimum value, a gap at the very bottom. And proving why that gap is there is such a big deal, it's one of the 7 Millennium Prize problems. So, how do physicists normally think about this stuff? Well, the conventional wisdom, the standard model of particle physics, basically treats the universe like it's a piece of software. It's a reality defined by these beautiful but very abstract mathematical fields. You could almost think of them like lines of code running a giant cosmic program. In that view, particles are just little expressions of that code, living in a perfectly smooth, continuous space. But what if that's looking at it all wrong? What if we've been focused on the software when we should have been looking at the machine itself? This brings us to a radical new idea, the hardware of reality. A new theory called the single bulk framework suggests that reality isn't a program at all. It's something physical, something with grit, something you could almost touch. And this slide just nails the difference. In the standard software model, a proton is this fuzzy, indistinct cloud of quarks and gluons. Its mass just comes from the energy buzzing around in that cloud. But in this new hardware model, a proton is a literal knot tied in the very fabric of space. Its mass isn't some abstract energy, it's the physical tension you feel in that knot. It's a completely different way of seeing everything. Now check out this visualization, because it really helps it all click. Up top, you got the standard view, smooth, abstract fields in a continuous space. But below, you see this new model. It's a grid, a lattice. It's chunky. It's granular. We've gone from pure math to physical mechanics. And see that equation at the bottom? It's not some abstract formula. It's all about elastic energy and something called frustration energy. So what in the world is that? Well, that brings us to a truly mind-bending idea, that space has a built-in stress. This model says the vacuum of space isn't empty, not even close. It's a physical structure, and it's a structure that's permanently under stress. It's geometrically frustrated. And somehow, that constant stress is what creates the rules of physics. So let's look at the first piece of that energy puzzle, elastic energy. You can just think of it as stiffness. Imagine space is like a tightly strung trampoline. If you try to twist it, it pushes back. This theory says the vacuum itself has a measurable stiffness, and get this, that stiffness is directly tied to one of the most famous numbers in physics, the fine structure constant, which is around 137. It's a measure of how rigid space itself is. But the real secret ingredient here is the second term, frustration energy. This is so cool. Okay, so in a perfect, tidy crystal structure, every point would have exactly 12 neighbors. Everything fits perfectly. But this theory says the vacuum isn't perfect and tidy. It's a randomly jammed together mess where the average number of neighbors is 14.4. And you just can't make that fit together without gaps or overlaps. The whole structure is under constant, built-in stress because of its own geometry. It's literally frustrated. And this built-in stress gets a fantastic name, the compliance tax. It's this background energy that exists everywhere, in every cubic centimeter of space. And if you want to do anything, like create a particle, you have to pay the tax first. You have to put in enough energy to overcome this background stress before anything else can even happen. And right there, that is the big aha moment. The theory basically says that to create a stable knot in the fabric of space, which is what a particle is, you first have to overcome all that internal stress. That potential barrier, that is the mass gap. All of a sudden, this incredibly abstract math problem becomes a physical, mechanical one. You can't have a particle with almost no mass because it costs a certain amount of energy just to tie a knot in a fabric that's already pulled taut. Okay, that's a beautiful idea, a really elegant story. But does it actually work? Can it make a prediction we can test? Well, this is where we put the rubber to the road. Let's try calculating mass from scratch. We're going to try to derive the mass of the lightest particle made by the strong force, a thing called a glue ball, using nothing but these supposed properties of space itself. The logic behind the calculation is surprisingly clean. It's like this. You take the highest possible energy in the universe, the Planck energy, and you run it through a gearbox. What are the gears? They're just the geometric constants of this space lattice we've been talking about. It's like a cosmic engine hooked up to a transmission, and the geometry of space steps that immense power way, way down to the scale of a single particle. And what's really amazing is that the whole calculation only needs 3 numbers. That's it. 3 inputs that all come straight from the geometry of this proposed vacuum. You've got your source power, the Planck mass, you've got that internal friction, the compliance tax, and you've got your main gear ratio, that stiffness factor of about 137. So you take those 3 geometric constants, you plug them into a simple algebraic formula, and the number that comes out the other side is 1.89 giga-electron volts. So the multi-million-dollar question is that number any good? Well, look at this. The SBF model predicts 1.89 GeV, the range that the world's most powerful supercomputers predict running the incredibly complicated calculations of the standard model is somewhere between 1.71 and 1.92 GeV. This simple back-of-the-envelope calculation landed smack dab in the middle of the target zone. That is pretty astounding. Okay, so the model absolutely nails the mass gap. That's huge, but can it explain anything else? A really good theory should. So let's see how it explains the fundamental difference between matter and forces, between knots, waves, and particles. And the explanation is just so physical and intuitive. In this model, bosons, the force particles, like a photon of light, are just vibrations of the lattice. They're like sound waves traveling through the fabric of space. And what can waves do? They can pass right through each other, no big deal. But fermions, the matter particles like a proton, they're different. They are actual twists, actual knots in the lattice. And what happens when you try to put 2 knots in the exact same piece of string? You can't. It's just physically impossible. And this simple idea has a profound consequence. It re-explains one of the most fundamental rules of quantum mechanics, the Pauli exclusion principle. You know, the rule that says 2 identical matter particles can't be in the same place at the same time. It's always been this strange, abstract rule that we just had to accept. But in this hardware model, it's not mysterious at all. It's just a simple rule of geometry called topological volume exclusion. It's the universe's way of saying, hey, you can't put 2 knots in the same piece of string. So, where does all this leave us? The model seems to explain the mass gap, and it gives a physical reason for the Pauli exclusion principle. That's a pretty good day's work. But was that first calculation just a one-hit wonder, a lucky guess? This brings us to our final section, a challenge to physics. Apparently not. The proponents of this model present what they call the triple crown verification, and this is where things get really wild. Using the same core geometric principles, they claim they can derive not only the glue ball mass we just talked about, but also the fine structure constant, that magical 137 number, and even the Hubble constant, which describes how fast the entire universe is expanding. From the tiniest subatomic scales all the way up to cosmology, all predicted from a single underlying structure. And as you can see, the predictions are staggeringly precise. And that's where we'll leave it. It all boils down to a single deep question. What is the fundamental nature of our reality? Is it a smooth, continuous program running on abstract mathematical laws? Or is it something more tangible? Is it physical hardware with grains and stiffness and maybe even a breaking point? It's a heck of a thing to think about.